Hi, this is Joel Smith with the SQ Stat Division, here to introduce our speaker for today. Pat Whitcomb is a chemical engineer, both a bachelor's and master's level from the University of Minnesota. But most of us know him with his role with StatEase, and StatEase, of course, is the developer of DesignEase and Design Expert software. And Pat was a founding principal and is currently president of StatEase as well. So we're very excited to have Pat here with us today. And he's going to be presenting on practical aspects of algorithmic design of physical experiments. And of course, based on his background, that's from an engineer's perspective. If anyone has questions along the way, there's a questions dialogue as part of the GoToWebinar interface. I encourage you to type those questions in. And I will, if they're very urgent, I'll interrupt the presentation. Otherwise, we're going to hold questions till the end and then pick a few out, see what we can get through. We are recording this, but we're not currently set up to share our recorded webinars yet. However, we will hopefully have that available in the near future, and we'll communicate that once those are available. So without any other delay, I'll turn things over to Pat, and we look forward to your presentation, Pat.
Okay, thank you, Joel. As Joel said, what I'm interested in is talking about algorithmic design, which is very popular nowadays. It's also called custom design or optimal design of experiments. And it's a very useful tool, but I think it has to be put into perspective of the bigger picture that you should be thinking about when you design experiments. So that's what I'm going to be talking about. And the objectives of my talk is that you understand why you would use algorithmic design and when it's appropriate to use algorithmic design, that you know the differences between the most popular optimalities that are used for algorithmic design, which currently are D or IV. IV is for integrated variance. You'll also see that with just I optimality. I and IV optimality are the same thing. You know what these two are and when you might prefer to use one over the other. I'd like you to know what the position of optimality, the choice of optimality is in a larger framework of what's required for a good or a successful design of experiments. And I'm going to present an example showing optimal design and a situation where it's imperative to use optimal design and provide some working recommendations. So in designing physical experiments, we need to think about what's required for a good design in general. So when we talk about designed experiments, we're trying to estimate some model. What properties would we like our design to have with respect to that model? What sort of optimality should you use? And I'll be discussing the I or IV versus D optimality criteria. I'll also mention G. There's others as well that are less commonly used. I'll talk about the practical aspects of algorithmic design. I'll show an optimal design example, and we'll have some conclusions and recommendations. So let's start off with what's required for a good design. Well, first thing is you have to think about what's the objective of the study. What are we trying to learn? What are we designing the experiment for? Then what you need to do is you have to state that objective in terms of the responses you're going to be measuring. So we have to be able to measure something to see if we've achieved our objective or not. And you have to think about how will those responses be measured. And in my experience doing designed experiments, both on my own for about 12 years and consulting with other people doing designed experiments for 30-some years, I'd say far and away the biggest reason I've seen designed experiments give unsatisfactory results is that there's inadequate, the ability to measure the response you're interested in is inadequate. I think that's often not thought about well enough. It's hard to improve something if you can't measure it. Okay, so we have to think hard about that. And then we have to try and define before we run the experiment what precision do we need to measure on this response. And I'll talk more about that in the talk. Now once we know what the responses are, we can start thinking about our process and think about what factors will affect those responses. And so we can pick the factors that we think are going to be the drivers for the responses we're interested in. Then we can think about what our region of interest is. That's the area we want to study, and also our region of operability. In doing designed experiments, I always think of it as, you know, it's like when people thought the world is flat. Our experimental worlds are flat. Doesn't mean they're flat in the sense they don't have peaks and valleys, but they're flat in the sense that if you go too far in any one direction, you fall off the edge of the earth. And so there's certain combinations of the factors we're studying that are too extreme, and we can't make a product anymore. And so we have to think about where those boundaries are. And so we have to make sure the region we're studying, our region of interest, is a subset of the region of operability where we can actually make a product. We have to think about what the behavior of the response or responses are we're going to be measuring, so that we can then pick the proper polynomial to model that behavior. So if we think it's just going to be a plane, we can get by with a linear model. If we think it's a twisted plane, we can get by with a factorial model. If we think there's going to be curvature, then we're going to need a quadratic model. If we think there's asymmetry in the region we're studying, severe asymmetry in addition to curvature, then we're going to need a cubic model. So thinking about the behavior we expect from the response we're measuring in the region we're studying then dictates what sort of a polynomial we're going to design for. What design should we use? Okay, so after we've done all those other things, now we can pick the design. I think a common mistake, particularly among novice experimenters, is they pick a design and then try to make their problem fit that design. So you should always be thinking about what you know about the problem. So use your first principles and use your experience dealing with the problem. Okay, so properties then we want the design we're going to run to have is, once we've done the other things and we've picked a polynomial, well, then of course we want the polynomial that we've chosen to be estimated well, the coefficients in that polynomial to be estimated well by the experiment we run. Okay, so we want to do that. In addition to fitting the polynomial, we want to have enough information so we can test whether it adequately represents the behavior of the response in the region we're studying. And we do that through testing for lack of fit. Lack of fit is bad, and we want the lack of fit to be insignificant. To test for lack of fit, that means we have to have more unique design points in our design than there are coefficients in the model. Then in addition to that, we need to have some way of estimating error that doesn't depend on the model. So one way to get that, the most common way, is to run some replicates. If I run some replicated experiments, I can estimate the error directly without making any model assumptions. If I'm not making any model assumptions, then that's a direct or pure estimate of what the experimental error is. We'd like our design we're going to run to be insensitive or robust to the presence of an outlier in the data, just in case something goes wrong with one of our runs. We'd like it to be robust to error in the control factor levels. Remember, when we say we're going to control temperature as one of our factors, we don't really control temperature. What we control is the set point of temperature, and every time we move away from that particular level and come back to it, we're going to get a slightly different temperature. And so there's always error in the levels of the factors we're studying. You know, we're shooting for targets, there's variation around those targets. Now, we'd like the design we run to permit blocking and sequential experimentation. We'd like to make sure when we are doing our analysis that we can check the assumptions that are made about homogeneous variance and we'd like to have useful diagnostics, including deletion statistics. I'll talk more about those in a bit. We'd like to generate useful information throughout the region of interest. In other words, we'd like to be able to get good predictions in the region we're studying, so we can actually look at the standard error, the predictions, as one measure of how good the design is. And the smaller those standard errors are, the better, and the more constant that standard error of prediction is throughout the region we're interested in is better. So we'd like them to be low and flat. Then, of course, I'd like to do enough runs to get those properties that are essential to having a good design, but I don't want to do an excessively large number of runs. If you think about adding runs to a design, every run you add adds more information, but it's not a linear function. Each run you add adds more information, but less than the run that was added just directly preceding that run. And so these things will kind of go up linearly till you reach a certain point, and then they kind of bend over and go asymptotic. And what we'd like to do is have enough runs so we can get up near that elbow, but not out into the part where we're getting little payback for additional runs. Okay, so this is an example of a design. This is called a central composite design. It's just a standard CAN design that's used for response surface methods. It's used to estimate a quadratic model. You can see the blue points on the corners of the square. That's a two-level factorial. You can see the green stars outside there. Those are called star points or axial points. You can see those occur on the axes of my coordinate system. So the blue corners of the square are at plus and minus 1. So the origin is that yellow point in the center with the 5 in it, and that's the 0, 0 point. And then the axial or star points occur along each of the coordinate axes outside the square. Okay. Now that yellow point in the middle is called the center point, and that's the point we replicate so we can estimate pure error. And we were going to replicate that 5 times. That's where there's a 5 there. And then if you look at the standard error of prediction, you can see that that center point that's replicated 5 times also helps pull down the error in the middle of our design space. If we only had one center point, we'd see a big bump where the error is high in the middle of our design space. Replicating that center point helps flatten out the error of prediction within our region of interest, which is the square enclosed by the factorial points. Now we can make contour plots of that standard error of prediction. And so this plot on the left is a contour plot of the standard error of the prediction. And the circle on the inside that's labeled 0.46, that contains 50% of the area of the square. Okay? So if we did what's called a fraction of design space plot, a fraction of design space plot is a plot of standard error, and it's the black curve, and it's a cumulative standard error, and it tells you how much of the volume in general in a two-dimensional problem, how much of the area in the region of interest has a standard error equal to or less than a given value. So you can see when I draw the standard error line 0.46 across to where it intersects that curve, and I look down to see how much of the area inside the square has a standard error of 0.46 or less. It's 50%. Likewise, the green circle, the next circle out from the center, where the standard error is 0.51, that encompasses 75% of the region of interest, or the square. So when I draw a line at 0.51 over to where it intersects the curve, I can see 75%. Then the last circle, most of which is outside the square, is just cutting off the 4 corners. Those 4 corners represent 5% of the area in the square. So the circle, the red circle, is encompassing 95% of the area in the square. So I can see when I have a standard error of 0.63, draw a line over to where it intersects the curve, it shows me 95% of the area has a standard error of 0.63 or less. Now what's nice about the FDS graph is if I go to 3 factors, then that instead of being an area becomes a volume, but it's still a one-dimensional plot. It's just that curved line that tells me the fraction of the design space or the fraction of the volume that has a standard error equal to or less than any stated values. And so that'll go up to as high a dimensionality as you want. And so it's a very nice way to look at different design choices. Okay, top choices for response surface method designs are the central composite design we just looked at. It's a robust, classic design designed to fit quadratic models. We can change those axial distances, the distances those star points are. So if I go back and look at the design, I could pull those star points in closer to the square if they were going to fall too far out. So let's say that my region of interest, the square, and my region of operability, where I can make product, are approximately the same size, then those star points fall off the edge of the earth, right? They no longer make the product. So I could pull those back in closer. If I pull them all the way in to the sides of the square, that's called a face-centered central composite design. And you put the star points on the faces of in this case, the sides of the square, and generally the faces of the hypercube when you have more than 2 factors. Okay, so those are good designs. Another alternative is a box-Benken design. That's a 3-level design where each of the factors have 3 levels. And then the third choice that I'm going to be talking about today is optimal design. So these are the custom designs you use, and they're the most flexible of the designs. And they're become essential when you have multilinear constraints. And that's the example I'm going to show you where we have some additional linear constraints. When you have designs that have categoric factors or factors with discrete numerics where you can only run certain levels of the factors. The reason they're important there is when you have a categoric or a discrete numeric to do all combinations, the designs just get too big. So you need a method to select an appropriate subset of all possible combinations, and that's what optimal design is good for. They're nice when you have models other than quadratic, because most all the CAM designs, for example, the central composite design, the box-Benken design, are designed for quadratic. So if you want to fit some other model, you probably have to build your own design. And it's also good to augment an existing design. Say you ran a CAN design and you found out that there is asymmetry and the quadratic model's inadequate, and you then need to add runs so you can fit, say, a cubic model. One way to augment that design with additional runs would be to use optimal design. Okay, so kind of getting back to the properties we wanted our design to have, we wanted the polynomial to be that the experimenter was designing for to be estimated well. That's what optimality is all about. It picks the points that are optimal for the design space you're interested in and the polynomial you specify. So that's what defines optimality. You want to get sufficient information to test for lack of fit. So you want to have more unique design points than models in the coefficient. Then we use a different criteria for picking those points. We use a criteria that's good for picking points for lack of fit. An example there would be we could use distance. So let's say we just had one factor x and we were designing an experiment to measure y, and we thought the response y was linear with x, and so we would just want to estimate the slope and the intercept. If I set up a design and said, okay, I have 2 levels, I have a low level and a high level, I want to fit the linear model between those 2 levels of x, the optimality criteria would say, well, the best points to run are the vertices. And if you ran 2 points, you'd have sufficient information to estimate the slope and the intercept, but that would be all. There'd be nothing to do statistical tests. The line would fit perfectly with 2 points. If you told it to do 4 points and you used optimality, it'd run the 2 vertices, but it'd do them each twice. If you said to do 10 points, it'd do each vertex 5 times. There is no point you can add that's more optimal than the vertices to reduce the error in estimating the slope and the intercept. Okay. So the problem is the optimality is kind of a self-fulfilling philosophy. If you design for linear, you're going to get linear. Okay. Lack of fit points then picked using distances is we'd say let's pick a point that has the maximum distance from the existing points. So you first pick your optimal points. Now we have the vertices, and we want to test if it's really linear. Well, the point that's farthest from those optimal points would be a point right in the middle. Now that's not a very good point to estimate slope and intercept, but it's an ideal point to see if that's really a linear model, really represents the behavior or not. Okay, so we're going to pick lack of fit points. We're going to pick replicates. So we're going to pick some points to replicate so we can estimate pure error. We want to be insensitive or robust to the presence of outliers in the data. That means that we have to have extra points beyond what are needed to just fit the model. And the lack of fit points and the replicates help us out there. We want to be able to be robust to errors in the control factor levels. Well, that's where if we do more than the minimum number of points. Of course, if I was fitting a straight line with 2 points, any error in achieving the levels of x's would be built into my model because those 2 points would be fit perfectly. If I had more than 2 points, then any error in the x's tends to get averaged out. And so having excess points helps me with that. You want to permit blocking and sequential experimentation. We can put blocking coefficients into our model and do optimal design to get estimates of the blocking coefficients as well. So that works well. We want to provide a check on the assumptions that underlie our model fitting. And so again, excess points help there to provide those diagnostics. If you have a minimum number of points, you don't get any diagnostics. If you have any points with leverage of 1, you lose the deletion statistics diagnostics. You want to generate useful information throughout the region of interest. Well, that's where sizing the design appropriately to get the profile you want is important. And then, of course, you'd like to have all these properties without too many runs. So we're going to strive for having enough, but not too many. Okay, so let's look at optimal point selection. The 2 main criteria, again, are integrated variance. That's called IV by some and I by others. Same criteria. And D-optimality. Okay, so first D-optimality. The reason it's called D is a D-optimal design minimizes the determinant of the X prime X inverse matrix. Now that big X, that's just your design. Okay, so whatever design you're going to run, expand it out for the model you're going to fit. Okay, so that's just a function of the design points you're running and the model you're fitting. So we can actually pick the design points for the model we're fitting to minimize that determinant. Then that gives us a D-optimal design. And what a D-optimal design does is it minimizes the volume of the joint confidence ellipsoid for the coefficients, or it maximizes the information about the polynomial coefficients. So if I was fitting a model that had 2 factors, x1 and x2, I'd get a coefficient for x1, beta 1, and a coefficient for x2, beta 2. If that design was orthogonal, then I could draw a confidence interval from estimate of beta 1. Okay, and that's what the 2 lines represent, some extremes on that confidence interval. I can do a confidence interval from estimate of beta 2, and the 2 lines represent the boundaries on that confidence interval. Then I get a joint confidence region for those 2 coefficients, and it's not that square that's drawn out by the limits on each coefficient individually, because the probability that it'll be in one tail of the distribution for beta 1 is very small. That you'd be in the tail of beta 2 at the same time, that's really small. So it turns out for an orthogonal design, instead of being a square, this is a circle. If the design's not orthogonal, in other words, your factors x1 and x2 are not uncorrelated, they're correlated somewhat, so the coefficients are correlated, then instead of getting a circle, you get an ellipse. Okay? What de-optimality does is it minimizes, with two of these, the area, but in general the volume of this joint confidence ellipsoid. So it's like minimizing the integrated error over the polynomial you're fitting. Okay? So remember, de-optimality is related to minimizing the error with the coefficients in the model. IV optimality seeks to minimize the integral of the prediction variance across the space. Okay, so these designs are built to provide lower integrated variance across your region of interest. This equates to minimizing that area under the FDS curve. Okay, so IV optimality is focused on predictions, and we're trying to minimize the error associated with the predictions in our region of interest, as opposed to de-optimality, which is focused on minimizing the error of the regression coefficients. Okay, so we'll start by looking at a little design where we compare point selection using IV and de-optimality. So we'll keep it very simple. We're going to build a one-factor design. We're going to design for a quadratic model, and we're going to choose all 12 runs using optimality as our only criteria. When I do that, the design on the left is the IV optimal design. You can see it put, for our 12 runs, it put 3 at each vertex and 6 at the center point. Okay, so that's our 12 runs there. Using de-optimality, it put 4 at each vertex and 4 at the center point. Okay, now the blue lines represent the average prediction variance, prediction standard deviation. And you can see that that's lower for the design on the left than it is the design on the right. So the average prediction error is lower, so that's more IV or I-optimal. Okay. If we looked at the fraction of design space for these two, you can see the IV optimal design is lower than the de-optimal design for probably 90% of the volume of the design space. And then the de-optimal design's somewhat better than the IV optimal design for maybe about 10%. Okay. Now, if you integrated the area under those two curves, you can see the area under the IV optimal curve is quite a bit less than the area under the de-optimal curve. Okay. And then over on the side is the minimum variance from the IV design, the average variance, the maximum variance. The same thing for the D, so you can see the IV has a lower minimum and average than the D. The D has a lower maximum, and that's that. You can see it's flatter out to the right. Okay. Now, designing experiments is not necessarily easy and should involve balancing multiple objectives, not just focusing on a single characteristic. Okay, that's a quote by Myers, Montgomery, and Anderson Cook from their book on response surface methodology. And so I'll give you my interpretation of that. When designing experiments, alphabetic optimality is not enough. Okay, so what else do we need? So let's talk about some of the practical aspects of algorithmic design. So again, we're going to look at an IV and a de-optimal design. We're going to build a one-factor design for quadratic, and we looked at picking 12 runs using optimality as the only criteria. This time I'm going to pick 8 runs with the optimality criteria and choose 4 of the runs as lack of fit points using the distance criteria. Remember, the distance criteria is going to put the new points as far away from those model points as possible. We do that by maximizing the minimum distance from an existing design point. Okay. So now if you look at the IV optimal design, the IV optimal design took its 8 points, put 2 at each vertex, 4 in the middle, and then the distance criteria just basically split the distance between those and put a point 1/3 of the way from the lowest level to the middle and 2/3 of the way from the lowest level to the middle, and the same on the high side, 1/3 of the way from the highest level toward the middle and 2/3 of the way from the highest level toward the middle. Now the D-optimal design put 3, 2, and 3. The lack of fit points end up at the same spots, 1/3 and 2/3 of the way between the extremes in the middle. Again, you can see the blue line representing the average standard error of prediction is a little bit lower for the IV optimal design than it is for the D optimal design. But the maximums, which are at the vertices, are lower for the D optimal design than they are for the IV optimal design. And so again, we could look at the FDS graph. We can see generally the IV is better. When you get out toward the ends, the D is better when we get out toward the very extremes. And so the D beats the IV a little bit. Now if we compare that to what we had when we had all 12 points selected optimally, you can see that from a strict optimality criteria, the D design with all the points picked using optimality beats the one where we had 4 lack of fits. Similarly for the IV, it's quote more optimal when I pick all the points. Now remember, we're fitting a quadratic. Both the D and the IV, when we picked all the points, have only 3 design points, the 2 end points, the 2 vertices, and the middle point. If it's not quadratic, you'd never know it because all you can fit is a quadratic. If there was asymmetry, there's no way to be able to measure that. By adding the lack of fit points, we're giving up some optimality, but now we can actually test whether the quadratic model actually represents the behavior of the response we're measuring in the region we're studying. Okay, so that's a good trade-off. I'd rather have less optimality, but when I get done, know that the model I have really represents the behavior, be able to do that test for lack of fit. Okay, let's just do one more comparison. This time we'll do a 2-factor design, and again, we'll split it. We'll design for a quadratic model. We'll do 14 optimal runs and compare that to 10 optimal runs with 4 lack of fit. And we'll do that both for IV and D. So if I do 14 runs picking all the points optimally, I get the design on the left. If I do 10 runs doing optimally, you can see it picked pretty much the same points but not as many replicates. But now 4 of the points are picked using distance, so it looks for the biggest spaces in the design where there aren't any runs, and it adds those in. And so you can see that the design on the right is what I'd call a more space filling. There's, design points over the whole space. And that's a better design from, I think, a practical viewpoint, even if from a narrow mathematical viewpoint of optimality, it's less optimal. So in this case, less optimal is better because there's more than alphabetic optimality I'm concerned about. I want to be able to estimate the quadratic model well, but I also want to test, does the quadratic model really represent my response to my region of interest? I can do that test with the design on the right. Okay, so and you can see in this case we're giving up very little in terms of optimality by doing the lack of fit points. And generally the larger your design is, the more factors you have, the less you're giving up by adding some of the runs as using distance rather than optimality. And we see very similar behavior with the D-optimal design. The design on the left is all 14 runs are picked using D-optimality, where the design on the right, we've got the 4 points that are kind of filling the holes in the design space. And it's not quite as optimal, but it's a lot better from a practical viewpoint as far as running a DOE where we're fitting an empirical model, which we don't know that it's right, we just hope it represents behavior. It's very important then to be able to test at the end, does it really represent the behavior? Okay. So adding lack of fit points. Okay, the design's not as alphabetically optimal. The lack of fit points fill the empty spaces. the ability to detect whether the model we're designing for actually represents the behavior that we're measuring, and we test that through lack of fits, is enhanced. So adding lack of fits a very good trade-off with picking all the points optimality with our optimal criteria. Okay. For estimating pure error in physical experiments, it's desirable to build an estimate of what the experimental error is. And we'd actually like to know what the experimental was at the time we were actually doing the experiments. And so one way we can get that is to replicate some of the runs. So the replicates provide an estimate of experimental error that's independent of any model assumptions. And so that's what we'd call pure error. We don't have to assume anything. Our estimate of error is pure. So adding replicates is again a good trade-off with picking all of our points optimally. Okay, so let's look at an example where we put these to work. So I'm going to look at just a three-factor example, and this is an example where we're going to do a spray coating of a stent. Okay, so a stent's basically a little screen that we put inside of a vessel to expand it where it's blocked, and we put on a coating which has usually has a drug in it that's released over time. So let's see if I can show a little movie of here's a stent being coated. So you can see there's a spray gun. There's a stent that's being rotated and moved back and forth under the spray pattern. And so the thickness of that coating depends on the flow rate of the material coming out of the spray gun, the pressure, and then the linear speed that it's moving back and forth through the spray pattern. Okay, now if we set up a design and we study those three things, and we pick low levels of each and high levels of each, we might recognize there would be some problems. Okay, at the vertex where the flow rate's low, the pressure is low, and the linear speed is fast, we may not get enough coating. Okay, so if we've got a real low flow rate, a real low pressure, and we're moving the stent quickly through the spray pattern, there's not much coating applied. Okay, likewise at the opposite vertex, when we have high pressure, high flow rate, and we have a slow linear speed, then too much coating gets applied. Okay, so the way we can handle that is through what's called linear constraints. So basically what we want to do is we've got this cube that's defined by our three factors. We want to identify the vertex that will fail. So in this case it's low pressure, low flow rate, and a high linear speed. That's where there's not enough coating. And then what we can do is we can back off from that vertex and say, okay, when the pressure is low, the linear speed's high, then I have to have a flow rate of at least 15. So that defines a point along that axis. Okay. Likewise, I can go when the other two are low, flow rate's low, linear speed's high, I can back off from that vertex, and I have to have a pressure greater than 6 before it'll work. So that defines another point along that axis of the cube. And then finally, when the flow rate's low, the pressure's low, then I have to have a slower linear speed, so I have to back off from that vertex down to point 3. Now those 3 points define a plane that cuts off that corner of the cube. Likewise, we can go up to the opposite corner of the cube where we had too much coating. We can identify that vertex where there was too much coating. We can back off each of the factors so it works when the other two are at their extreme. Those points along the edges of the cube define a plane that cut off the corner of that cube. Okay, so we end up with knowing what these points are. We can write an equation that prevents us from moving outside that constraint plane toward either vertex. Okay. Now, what we want to do is we need to build a design. So here's a suggestion for a practical algorithmic design. And I call it practical because it's not optimal in the sense of alphabetic optimality, because we're going to give up some alphabetic optimality to pick lack of fit points and replicates, but those are, from a practical experimental viewpoint, those are very good trade-offs to make. Okay, so given how many factors you want to study, in this case there's 3, and the number of coefficients in the model you're going to fit, in this case we're going to design for a quadratic model for 3 factors, so there'll be the intercept, that's 1. The 3 linear coefficients, so that's 1 plus 3 is 4. We've got the 3 two-factor interactions, AB, AC, BC. So that gets us up to 7, and then the 3 squared terms, A squared, B squared, C squared. So that means we're going to have 10 coefficients we're going to estimate. So we got to pick a minimum of 10 points, and we'll use the optimality criteria to pick the 10 very best points for estimating those coefficients. Then we're going to add lack of fit points, and it turns out that 5 is kind of a nice number in statistics. If you were to look at any statistical table with degrees of freedom, what you notice is if you're looking at like a t-test or an f-test, is the degrees of freedom increase the size of the statistic, the critical value of the statistic gets smaller, but each degree of freedom you add, it gets smaller by a smaller percentage than it did for adding the point just before. It turns out that these things drop pretty rapidly and then asymptote out, and that elbow is right about 5 degrees of freedom. So we get most of the benefit we're going to get by adding 5 points. So we're going to add 5 lack of fit points. Okay, so we pick P model points using the optimality, then we pick 5 lack of fit points using distance. And you could use other criteria. You could try to make it robust to the quadratic model. So I'm going to pick 5 lack of fit points instead of using distance. I'm going to pick them so I can estimate some subset of cubic coefficients. But for this example, I'm going to use distance. Then after you've got those 15 points and you say, okay, I'm going to pick 5 points to replicate, it doesn't matter which points you replicate for estimating error. So we can go back to using the model criteria and say I'm going to pick the 5 points to replicate where those replicates add the most information about the quadratic model. Okay. Then what we can do is we can evaluate the precision of the starting design using an FDS plot, and we can actually size our design for the precision we want in our predicted values. And if that precision is not good enough, then what we could do is add more runs, and we could decide when to quit adding runs when we have the precision we require. Okay. So this is just an example of a 10-point IV optimal design with 5 lack of fit points and 5 replicates. So there's 20 points on here, not actually 20 points because some of them are run twice, but if you added up all the ones that aren't there, but the points that are single, and then 2 for each one that has a 2 by it, you'd get 20 runs. Spread across that cube with the 2 corners cut off. Okay. Then we could do a test and say, is the optimal design precise enough? Well, let's say this response, we wanted to estimate the mean value within plus or minus 0.5. Okay, so I want to be able to predict the response I'm measuring, and if I do a confidence interval on that prediction, I want that confidence interval to be plus or minus 0.5. So 0.5 is a half-width of the confidence interval. Okay, so we can use that. That's D, the half-width of the confidence interval. You have to provide an estimate of what the experimental error is. So in this case, if we're measuring kinetic drug release, or we're measuring thickness of the coating, or you're measuring something else, you have to provide some estimate of what the experimental error is expected to be. In this case, from historical data, we've coded stents before. We know that standard deviation is about 0.3. If you plug those in, you can then calculate the standard error that you need to get the precision you want, so that half width on the prediction of the mean has a confidence half width of plus or minus 0.5 or less. Then you can draw that blue line in. You can look at where it crosses the curve, and you can read off that axis. It's actually over in the legend here. That 91% of the design space has a standard error that will give us a half width of the confidence interval of 0.5 or less. And so that means 9% we're not going to get that. And sort of like with power, if you're familiar with power, when we do factorial designs, you'd probably want the fraction of design space to be at least 80%. So in this case, the kind of the minimum number of runs that give us a good design also give us enough precision. So we're in good shape. Okay, so that's my example. So to summarize, good choices when you're doing response surface methods is central composite and the box banking. If you have a cube, use a design that's based on a cube. These designs are optimal in many senses with good properties built in as well. So use them if you can. But if you can't use those, for example, we couldn't run some corners on our cube, so we had to use multilinear constraints. Once we put those in, there is no canned design we could use. So we can use optimal or custom design to give us a good design. I didn't show examples, but again, when you have categoric factors or designs with discrete numeric factors, actually this design, we didn't go into all the details, does have a discrete numeric factor as well. When you talk about passes, that's not in the design we looked at, but in the original design, I simplified it for this talk. One of the factors was also, do we pass over the stent with 1 pass, 2 pass, 3 passes? Okay, so we go back and forth over the stent like the little movie. How many times do we go back and forth? Well, that's called a discrete numeric, because it wouldn't make any sense to go over the stent halfway and stop. You know, you have to go 1 pass or 2 passes. You can't go 1.5 passes. Okay, so when we want to design for models other than quadratic, most of the CAN designs are based on quadratic. So if you want to fit something else, a reduced quadratic, a special cubic, a cubic, whatever, you could use optimal design. And then if you've run a design and found that it doesn't adequately model a space and you want to augment that design with additional runs, Optimality is good for that. You always want to choose a design that fits the problem. And so when I teach design of experiments, I always tell people, if you find yourself that you're changing your problem to fit a design you want to run, you're probably doing the wrong thing. You should be changing the design to fit your problem. And if you don't know how to do that, then you should seek some expert advice. Okay, so we want to make sure that the design we run fits our problem, and that's what optimal design is really good for. And then we can size our design for the precision we want. So we saw we could actually look at how precisely do we want to be able to predict the response we're measuring. And we can measure whether or not we're going to have a chance of doing that using the fraction of design space prior to running the experiments. Okay, so remember these properties we wanted. Being able to estimate the polynomial well, that's what optimality is all about. Testing whether or not we the model we fit represents the behavior in the region we're studying. That's what the lack of fit points are for. Getting an estimate of pure error, we can use replicates, and those can actually, again, be picked using the optimality. So the points we replicate are the ones that provide the most information about the model we're fitting, or if we're sizing for precision, the ones that do the most to reduce the standard error of the prediction. Lack of fit and replicates are kind of extra design points beyond the minimum needed to fit the model, so that makes it more robust or insensitive to outliers in the data. They also are excess design points. They help with averaging out the variation of the factor levels around their set points. We didn't show it, but we could have added, we could have done our set of experiments in 2 different time periods and blocked it. And we could have used optimality then just by including a blocking coefficient in our model as we're building our design. We want to be able to provide checks looking at the diagnostics. And again, you got to have excess design points to calculate many of those diagnostics. We saw a little example how we could size here for the precision we wanted. You don't want to have an excessively large number of points, and so this next slide is the default I use when I start designing an experiment is given how many factors you want to study and what polynomial you're going to fit. That tells you how many coefficients you have to fit, and that's the absolute minimum number of points you can have, so I'd pick those points using optimality. I'd then say, okay, now I need some extra points so I can see if this model I just fit really represents the behavior, so I'd add some lack of fit points. Then I'd say, well, I also like to have an estimate of error, so I'm going to replicate some points. I'm going to add 5 replicates. And so starting with that, absolute minimum number of points to estimate coefficients, 5 lack of fit, 5 replicates is where I'd start. Then I'd use that FDS to see whether or not it's going to give me the precision I want, so I'd define the half-width of a confidence interval. In other words, I want to be able to predict the mean response plus or minus some number of units, D number of units. That D is the half-width of the confidence interval, and then I can see what fraction of my design space I can achieve that. And if that's, say, 80% or more, I'm probably in pretty good shape. If it's not, then I can go back and rebuild the design, putting in more model points. If you have got 5 lack of fit and 5 replicate, you're getting out there onto the asymptotic part, so more points there aren't going to help. So if you're going to add more points for precision, add them as extra model points, because those are the ones that are picked to minimize the precision. So what's really important to remember is you have to think about identifying what the opportunity is, define your objective, and just saying you want to improve something is not an objective. You have to actually state the objective in terms of the responses you're going to be measuring. For each one of those responses, you have to think about how precisely do I need to predict this, and define the half-width of that confidence interval, say D. So I want to know the mean value plus or minus some amount. And that D, that plus or minus amount, is the half-width of your confidence interval. Estimate experimental error. With those, then you can calculate the fraction of design space that's precise enough. You then select input factors and ranges to study. Select the design. Evaluate the precision with the FDS plot. Examine the design layout to ensure all the factor combinations are safe to run, are likely to result in meaningful information. So it's easy to set up a design without thinking about the extremes, and so you really want to, before you run any design, is look at each run and try and anticipate what will happen when you make this run to make sure you don't have failures that could have been prevented. And so like with the stent coating, when we looked at those combinations, we said, oh, these combinations are going to result in stents that don't have enough coating. So we went back and we modified our design so that we wouldn't generate those stents. And at the opposite vertex, we said, oh, these runs are going to have too much coating. So again, we put in constraints. So we modified our design space so we wouldn't get stents that have too much coating. What should you use, D or IV? Well, IV is focused on the precision of the estimation of the prediction. So how well can I predict? When we're doing response surfaces, generally what we're doing is we're doing contour plots, 3D plots, we're doing multi-response optimization. All those things are based on predictions from that model. Okay? So our focus is on prediction. We should use IV optimality, which focuses on giving us the most precise predictions. When you're doing screening, so I'm doing two-level factorial design, for example, and I want to figure out what factors are important. Okay, now my emphasis more on the factors than on the prediction, and that's the same as saying I'm actually more interested in the coefficients. The coefficients represent the effects of those factors. Okay, D-optimality is focused on precise estimate of model coefficients. So when I'm doing screening, it's the ideal criteria to use. The other place you could use it, although this doesn't occur a lot, is when you already know the model. So when you're doing mechanistic modeling. For example, when I used to do roll work, sometimes I'd be sizing a heat exchanger for scale up on a process. I knew the model for heat exchange, I just didn't know what the coefficients were. Okay, in that case, my emphasis again was not on prediction, my emphasis was on the coefficients. I already knew the model, so then I could use D-optimality for that. Keep in mind when you're doing this that no alphabetic optimality or sophisticated statistical analysis or even any computer software can ever make up for studying the wrong problem, measuring the wrong response, not having adequate precision, studying the wrong factors, having too many runs outside the region of operability. You know, that's why we want scientists, engineers, chemists, biologists to use the first principles they know about the products they're studying, to use their experience, and we want them to be designing the experiments. Statisticians, as statisticians, we can help you then design an experiment well, but I can't ever design an experiment for someone else because I don't have the subject matter knowledge. So remember, it all starts there. And I always think of design experiments as an amplifier. If you've got reasonably good subject matter knowledge, you're going to do really well. If you have really bad subject matter knowledge, then you're going to be feeding noise into the amplifier, and you'll just get more noise out. Okay, here's some references. And thank you for your attention.
All right, well, thank you, Pat. If anybody has any questions they want to submit, now would be a great time. We actually haven't had any come up. So you've obviously done a great job of explaining everything. If anyone's interested in getting slides from this, you can contact either myself, which the email for that will be host@asqrd.org. That will appear in your follow-up. Otherwise, Pat's contact information is here, and I'm sure he encourages you to contact him with questions, or he wouldn't be putting this up. So thanks, Pat.
Joel, also, I've already posted the view graphs on our website. So if you go to, I don't know if I can get to our website from here. Can you see this?
Yes.
Okay, so if you go to our website under Publications, Webinars, and you go down to Past Webinars, the very top one there are the slides from this talk.
Excellent. Perfect. So there's a quick way to access things. So
you can have immediate access. You can look at them online, or you can download the file. It's kind of a big file if you go to download it because there's a lot of graphics in it, but they're there already.
Excellent. Well, we thank you for having that posted ahead of time. So, well, then we'll go ahead and conclude things now, and I encourage everyone to keep watching for our postings on our next webinar, which will be in November. We'll have the details out about that shortly, and thanks